Hi everyone, this is Professor Burgasser, and in this video we're going to look at how we can use our gravitational force law plus approximation methods to get an idea of the forces that give rise to tides on our planet. Now the tides arise because the gravitational force law varies with distance, and we have a force that's acting on us by both the sun and the moon. And of course that gravitational force, as it varies across the Earth, is going to give rise to different amounts of force depending on whether you're on the near side or far side from the moon or from the sun. So we're going to take the example of just the tides arising from the moon. And so I've done a schematic here, which is definitely not the size. All right, we're talking about many orders of scale here that we're hiding. But the a simple sort of setup for this is that we've got the Earth and the moon as the green circles here, and they have these finite sizes. And we want to look at what the gravitational force gradient is, the change in the gravitational force is across our planet with respect to the moon. So at these, we can look at sort of three different points along our planet: the side that's closest to the moon, the center, and the side that's furthest away, and write down what those gravitational forces are. So if we look at the, let's take the center one first. That's just going to be g times the mass of the Earth times the mass of the moon divided by this Earth-Moon distance squared. All right, just looking at the magnitudes of the forces. Over here, we are a little bit further away, so the force is g mass Earth mass moon over the Earth-Moon distance plus the radius of the Earth. All right, we've got that extra little piece of distance there. And of course, this expression is going to be the opposite. We've got g mass Earth mass moon divided by the Earth-Moon distance minus the radius of the Earth. So question is, what is the actual difference between these three forces? Right? How big of a gradient in force are we actually talking about? Well, we can come up with that number by using our approximation methods, using our Taylor approximation. Just to remind you that the approximation that we use for this is if we're trying to evaluate a function around some point and we're looking at it just slightly away from that point. So we're evaluating a function at some point A, and we want to look at just a little bit off from that. Well, this is approximately equal to evaluating that function at that point A and then adding a derivative of that function, again evaluate at point A, times our little step forward. So this is assuming that there's sort of a very small linear relationship around that point, and we're just taking a little bit of a dive over from our initial starting point. Well, in this case, our function is 1 over r squared, and the derivative of that is equal to minus 2 over r cubed. So we can write down, let's write down actually both of these expressions combined, because we can just do that with a plus or minus sign. So r Earth moon plus or minus r Earth quantity squared. Well, if a, so we'll let a equal the Earth moon distance, which is the larger number, and delta is equal to the Earth radius, which is the smaller number. Well, then this is just equal to evaluating this expression at the middle. So that's at Earth-Moon distance squared. And then adding this derivative, but in fact, because it's a derivative is negative, we're actually subtracting, so be careful here, minus the same expression, GME m moon, and now over Earth-Moon cubed, times our little change that we've added here, which is just the radius of the Earth. And if we combine these things, and we have to keep in mind this is plus or minus the radius of the Earth. So if we combine these things together, we group our terms, we get our center expression for the force times 1 minus plus, and I forgot there's a 2 here, so make sure that's in there, minus plus 2 times RE over r Earth moon. Right? So the expression for the force at these endpoints is just equal to our center force plus this small correction factor. And the ratio of these numbers is about 60, all right? The Earth-Moon radius is about 60 times that of the Earth radius. And so this is about a 3% correction. All right? So what does that mean? That means that the force between the leading edge or the falling edge relative to the center of the Earth is about 3% the total force that's keeping the moon in orbit, for example, because that's the same force acting between the Earth and the moon. So it's actually a pretty substantial force, and it's enough to literally pull both our atmosphere and our water and our land to some degree in the direction of the moon. That's the close side. The other side is that you have less force acting over there, so it's actually falling away. It's trailing behind by essentially the same relative force. Now, in reality, the way our Earth rotates, if we're spinning around on our axis, it takes some time for that water to respond to that extra gravitational force. And in fact, our tides are slightly shifted around. They're rotated around because the Earth is rotating faster than the moon is revolving around us. So our tides are actually leading our moon a little bit. And in fact, the interaction between those tides and the moon is something that's slowing our Earth down over time. So this is just an example of how we can use our approximation methods to calculate something about the tidal force and how it depends on the distances involved. So instead of having the Earth-Moon, I could always look at this similarly with the force that's exerted by the sun, and we'll get a slightly different expression because we're looking at different distances between the Earth and sun and different sun masses, of course. The interesting thing is in the end, you'll find that that tidal force, this extra term at the end, is very similar in magnitude because the sun is so much further and so much more massive. Those terms cancel out. And so in the end, the moon and the sun exert roughly the same tidal forces, roughly the same expansion forces on our fluid parts of our atmosphere because of this extra correction for the gravitational force varying across the surface of the Earth.